This is section 9.3, infinite series. So what is an infinite series? Remember, series, you're adding up a bunch of things. So in an infinite series, you're adding up an infinite number of things. So if you see, you start with the first item and you go to infinity, so you're just going to keep on adding without an end. And then there's a concept of partial sums. This is just adding the first term. S sub 2 is adding the first two terms, so that's a partial sum. You're doing part of the whole series. S sub 3 is the first three terms added, and so on and so forth, and you get the picture. And so S sub n is adding the first n terms. Now, before we do an infinite series, we're going to look at the geometric sum, and we'll look at the geometric series later. But this is a very specific type of a sum. And so what does it say? Each term is a constant. So the constant is your starting point. And you multiply, take that back. Your previous term is your starting point. You're going to multiply by the constant to get the next term. And you're going to multiply by that same constant over and over and over. So here's how it looks. You have your first term, a. To get the next term, we're going to multiply by the constant r. So you multiply by r to get the next term. Well, you multiply by r again, so now we're going to have r squared, and you just keep on going. You multiply by the same number over and over and over, and why n minus 1 when there's n terms? Because the first one is just all by itself. So to get the second term, you multiply by r once. To get the third term, you multiply by r twice, so that r, the number of r's, is one less than the number of terms because the first one doesn't have one. So that's the notation for that and what's going on there. And you need to be very comfortable with summation notation. Make sure you understand why that matches that. And if you're not comfortable with that, you need to sit with that and get comfortable. Okay, r, that's the number that you're multiplying by to get the next term. That's called your common ratio or just your ratio. And here's why it's called a ratio or common ratio. Because if you take any term and divide it by the previous, you'll always get r. So like this one, ar squared divided by ar, the a's will cancel, one r will cancel, getting you r. So it's a common ratio that must be throughout the whole series. So this is just an example. This section's pretty quick. You have a geometric sum. There is your ratio. That's where you can multiply each time. That is your starting number. And that's how many terms you're going to get. So clearly you can start with 0.9. But 0.9 times 0.1 is going to be 0.09 to get your next term. Well, how do you go from here to here? You multiply by your r again, and you're going to get 0.009. But if you multiply by this again, you're going to put 0.0009. This is a summation notation. You probably want to plug these in and make sure you understand where that comes from. So we can add these up. Now, here's a formula that you need to know. The sum of a geometric with n terms. So the partial, or actually, the sum of the first n terms of a geometric series. And it's just this formula here. It's the first term, a, and then 1 minus r to the n, where n is the number of terms total, over 1 minus r. So that's what you're going to have to know. So we're going to try this formula on the previous example. The previous example, we had 4. The sum of the first 4 terms, they told us 4. And that's going to equal a. What is a? A is the first term, which is 0.9. And then 1 minus r to the n, r is 0.1. The nth power is 4 because we have 4 terms, tells us right there. And we're going to divide that by 1 minus r, which is 0.1. I don't have a calculator on me, so hopefully this is going to be too crazy. that's going to be what, 0.0001? I'm kind of sad. I'm in panic trying to find a quick calculator. I think I have one here. So we'll calculate this. So it's 0.1 to the what power? 0.1 raised to the fourth power. Okay, 0.0001. I'll go ahead and write this down. 1 minus 0.0001 over 1 minus 0.1. That's still there. So 0.9. What's that going to be? 1 minus that. That's kind of crazy. Let me do that here. So this could be 0.9999. 0.9999. And 1 minus 0.1 is just 0.9. So, wow, these 0.9s cancel. And we get 0.9999, which makes sense. That's a decimal, by the way, kind of ugly. It makes sense because what's this? Add them up. It's 0.9999. So that formula worked rather nicely. And that's the example of how you use this formula. So that's for a finite number of terms. Now, a geometric series. The only difference between the previous problem and this one is the number of terms. This is an infinite geometric series. Notice the infinity there. And the ... it goes forever. And so the sum of all of the terms forever is represented in this by summation notation. So here is the theorem. Here is probably the most important point of this lesson, is the sum of a geometric series. So it's given right here. So a couple things must be true. A must not be 0. Because if you start with 0, it's just going to be 0 plus 0 plus 0. It's kind of dumb. R has to be a real number, no imaginaries, right? And then here, absolute value of R must be less than 1 for this to work. If that is true, the sum of infinite number of terms is just the first term divided by 1 minus R. But this must be true. The absolute value of R must be less than 1. I'll kind of give an explanation in a second. If your R is greater than or equal to 1, the series will diverge. So you're out of luck there. So here's an example I'm going to give. So if you have a total distance, I did this in class, 20 feet. I'm going to can't even talk. I'm going to walk halfway. I'm going to walk 10 feet. Okay? And then I'm going to walk half of that, what I just walked. I walked 10, so this time I'm going to walk 5 feet, half of the previous distance. And then next, I'm going to walk half of that, which is 5 over 2 feet. I'm not going to put the feet because I'm running out of room. Then I'm going to walk half of that distance I just walked, which is going to be half of what's left in this case, 5 over 4. And I walk half of that distance which is left, which is 5 over 8. Now, it should make sense if I'm only walking half of the previous distance, I'm never going to reach 20 feet. I'm going to get closer and closer and closer, but I'm never going to touch. Okay? So that's the concept of how can you add an infinite number of things yet not go to infinity. Well, here's an example. You're going to add some numbers forever and ever, and it's only going to approach 20. And it's not going to even reach 20. It's going to get closer and closer to 20. So that's how an infinite number of things can add up to an actual number. Okay? But think about this. It worked when I went half of the previous distance, right? I went half each time, and it prevented me from going there. Now, I can go 0.9. As long as I only go 0.9, I will never get there. But if I go the same distance each time, so the first time I went 10, if I went 10 again, I'm at the wall, 10 again, I'm through the wall. So going the same distance each time, in other words, multiplying by 1, having a common ratio of 1, does not work. So that's why if r is 1 or even bigger, it's not going to work. So if it was bigger than 1, say it was 2, first time I walk 10, double that, I'm going to walk 20. Clearly I'm busting through, and as I add more, it's going to go forever and get bigger and bigger and bigger. Not going to work. So I need to make sure it's only going to work if my common ratio, the absolute value of it, is less than 1. So I'm going to give you 6 examples. Of these 6, the question is, which one of these converge, which ones diverge, and if it converges, what does it converge to? So first one's easy. First one diverges. Why? If you look, you should recognize this is geometric because you have a r to a power. So that's how you're going to recognize geometric. But what's your r? R is 1.1. What does it say? If the absolute value of r is greater than 1, it's going to diverge, so that diverges. This one's weird. Some of you might say, oh, the base is e, divergent. E is bigger than 1, divergent. But that is a minus k. We need to rewrite this in a way that is geometric. Geometric would be this, but that's still not geometric because technically it should be some number raised to the k power, and that's 1 over a number to the k. So now we can rewrite this one more time, and it's going to make sense. Should make sense. I'm going to put this in parentheses raised to the k. Now hopefully you are convinced that that is equivalent to that. So this is my r, which is less than 1, to the kth power, so I have a geometric. And to find the sum, when k is 0, what value am I going to get? If I put a 0 there, I'm going to get 1. So a will be 1, my first term. So what's the sum of an infinite? Well, we just had the formula. It's the first term, 1, over 1 minus r. My r is 1 over e. Now we can simplify that. I'm not going to for the sake of time. I would just multiply everything by e. But let's move on. All right, so this, you might say, hey, we just did that. Here's my answer. Quite ugly answer, in fact. Let me clean this up. But there's a difference. Yes, it'll come out to be like that, but do you see the difference? K starts at 1 and goes to infinity. So I'm going to have 1 over e to the k power, just like I did over here. It's going to repeat here. But to find my first term, I got to be k equals 1 to find my first term. That's going to be 1 over e. So that's the difference. We're going to use the same formula here, a sub a over 1 minus r. So this should be a, which is 1 over e, over 1 minus r, but r is 1 over e. Now I'll go ahead and do this one. If you want to tidy it up, you're going to multiply by 1. My 1 is e over e, and that's going to get me 1 over e minus 1. Kind of prettier, not so many fractions and fractions. All right, 3 more, and we are done with this video. Right on. Okay, I don't know if I copy this right, but we're going to have to deal with this. This k is supposed to be on the outside. My apologies. Just realized that k is out there. So, that's a geometric because we have an r to the k power. Does this converge or diverge? Looking at the rule, the absolute value of r must be less than 1. Well, the absolute value of that is 0.75, which is definitely less than 1. So yes, this converges. What does it converge to? The same old process we've been going through. Plug in the first k. We're going to get 3 times negative 0.75 squared. All right, I'm going to have to cheat and do that separately. I'm not smart enough to figure this out in my head. Okay, let's see what I'm getting. Then I have to multiply that by 3. Wow, craziness. So my A is going to be 1.6875. I don't like that. That just seems crazy, and it's going to be too much work. So the sum of this infinite series is going to be the first term over 1 minus r, but your r is negative 0.75. So it's actually going to be a plus there. Okay, so that's that one. Hopefully I'm doing these right. We shall see. This is funky. Is that geometric? It doesn't look geometric. So we need to be able to rewrite it. So geometrics can have a constant and your r to a power. Anything like that is geometric. And so we can rewrite this. So this can be rewritten like such. Using your algebra skills. 3 times 4 over 7 to the k power. Now, I'm not going to finish this one off. This is more of an introduction. But that's your r. Your r to the k. So you have an r. You can find the first term. If you plug in 3 right here, that will get you the first term. So your sum of the infinite number would be your first term divided by 1 minus r. And your r would be 4/7, so therefore it's going to converge. So that's how you'd go about that. I'll work some of these in class tomorrow, so let's just look at these. Now this one, going back to this is a very common thing, manipulating using algebra to get something that doesn't look geometric to be geometric. So in a geometric, you have a constant, an r to a power, and that power is going to be the index variable. Okay, so the last one, is this proper form for geometric? And the answer is no, because of the minus sign. So I would rewrite this like this. It would be 3/4 to the k. So some might look at that and say, oh, that diverges because that is greater than 1. But know that minus sign changes these to that. And 3/4 absolute value is less than 1. So this series does converge. And I will do this one for you because it's a little bit easier. So if k equals 0, I'm going to get my a equal to 1. And so the sum of the infinite series is going to be the first term, 1, over 1 minus r, and r is going to be 3/4. So this will be 1 over 1/4, which is 4. And hopefully that's the right answer. But that is a quick introduction to geometric series. We'll do some homework tomorrow night, but today or tomorrow, depending on when you listen to this, the next lesson I should say, we'll be doing some sample problems like these. And that is all.